Today's webinar will focus on training for EPA's Freshwater Explorer tool. The Freshwater Explorer tool provides information on the status of water resources for networks of streams in the U.S. color-coded for measured freshness, such as low salt and mineral content. This training webinar will demonstrate how to perform geographical searches and visualize background and measured data for water quality parameters using the Freshwater Explorer. This combination of information is useful for states to work with communities and regulated entities to find the right balance of protection and use of fresh water. Our presenter today is Dr. Susan Cormier. Susan is with EPA ORD Center for Environmental Measurement and Modeling. And I want to thank you, Susan, for doing this training for us today. And if you have a question, please type it into the Q&A pod, and once the presentation is over, we will go through as many questions as time allows. And I see that Erin has put the slides for today as a downloadable file in the webinar platform. We will also be posting those slides to the EPA Research website, followed by a recording. So with that, I'm going to turn it over to you, Susan.
All right.
Yes, I hear you good.
Okay, great. Okay, well, thank you for the kind introduction, and thank you to everybody for tuning in. I know it's a busy season, and I appreciate your interest. So what I'm going to cover today is a little bit of what is the Freshwater Explorer, a little bit about what you can do with it, and a little bit of the science underneath it so that it won't be too much of a black box when you use it. And needless to say, even though my name is the only name on the front of this presentation, this was a team effort. So first of all, why did we even decide to make the Freshwater Explorer? And what we wanted to do was to provide easier access and visualization of aquatic information. There's an awful lot of information that's available on the Water Quality Portal and other EPA resources. And sometimes it's hard to connect the actual measured data with other information. And that's why we decided to start the Freshwater Explorer. It's in its early iterations at this point, and we hope that it will grow and have more content to it as time goes on. Right now, what it does contain is a stream network that's color-coded for background conductivity and point locations of measured conductivity and total phosphorus. And as we go through the slides, I'll refer back to this little outline of what we're going to do in terms of talking about the development and the navigation and examples and what's next. So first of all, what was the problem that we were interested in? We knew that there were higher levels of minerals in waters and that this could cause harmful algal blooms, especially if it's phosphorus and nitrogen. It could affect aquatic wildlife for any of the parameters that could be potentially problematic, and increase costs for making water suitable for drinking and other purposes. So our approach was to design an accessible and intuitive interface to visualize and explore water quality in a map format. So this is the important component of this, is that it is spatially explicit. So the actual result that we have to share today is a network of streams in the U.S., and they're color-coded for the measured freshness. And what we mean by freshness is a low salt and nutrient mineral content. And then it's possible to explore that background network of streams that are color-coded on a predicted model of what that freshness is to what is actually measured in locations. And the impact of this is that it's useful, as was Lisa mentioned, that for states to work with communities and regulated entities to find the right balance of protection and use of fresh water. But it's also useful for anyone who wants to understand what's going on and start to think about ways to appreciate the effort that has gone into data collection and what it means for a locality or for the country. As I've mentioned before, it is a network of color-coded background conductivity, and then the measured values of conductivity and total phosphorus on top of that network. But seeing it makes it a lot more easy to understand. So here you can see, what is it? What you can see is when you get to high resolution, there's a network of streams and they're color-coded. And the color would indicate whether the stream was in the warmer colors like orange, higher predicted conductivity background for those streams. So this would be what we would predict for this stream in the absence of additional inputs from human activity. Whereas you can see in these blue streams, these would be low background conductivity. And then there are dots, and you can see one dot here, a purple one, and that indicates an actual measurement point. And there's a pull-down menu that comes on when you click on the dot and gives you information about those measurements from that location. If you click on a stream, another pull-down menu will come down and explain what the predicted background is likely to be. So over here on the right, you can see here are all the measured points for, in this case, conductivity in streams across the United States, taken from the Water Quality Portal. And here you can see what the predictions are. And what you can see right away is that there are certain parts of the country that are naturally higher in conductivity and other places that are lower. And that pans out in the measured values as well as the predicted. However, you can also see that some places tend to have higher conductivity measurements that were measured in the streams than what would be predicted. And we'll go into that in more detail later in the presentation. So the next thing I'd like to talk to you about is how we developed it. And the important thing here is anybody who has worked with very, very large data sets with millions of entries and hundreds of people entering that data into a system, there are bound to be issues. And so we have tried to curate the data that's in the Water Quality Portal for these two parameters to make it easier to use. So in this table, you can see the process that we use to curate that information. We identified a number of issues and the actions that were taken. And all of this information is available in sections that describe the data sets and how that information was modified. So for example, a value for nutrients or conductivity is never can be less than 0. In other words, a negative number. And so anything with a negative number, we simply removed it and it does not appear in the data set. Sometimes there are ambiguous units that are reported, and we removed those, and then we also made sure everything was converted into just one unit for conductivity, for example, where we just report microsiemens per centimeter. Sometimes the units were reported as microsiemens or millisiemens, and we made sure that those are all in the same units. Everything is reported as microsiemens per centimeter. Sometimes when data is entered into a system from one system to another, the mu sign is interpreted by the computer program as the letter M, because mu is M in Greek. And so what would happen is sometimes something that was measured as microsiemens would be reported as millisiemens, and of course that would mean a big error of 1,000 difference. So those kinds of things we try to identify and flag. We can't change any of the data that's in the WQX data sets. Those are your data. And so all we can do is indicate that there might be an issue by coloring them gray. So same thing, it can flip the other way, where we might have a marine systems that are in it, and you're really just interested in streams. And so we, again, color those things gray. Now, sometimes these numbers are real, and I'll show you one of those examples as we come along. We still color them gray, but we can check them, and sometimes they're true values. So here's an example where one state's data set was entered into the system, and all of their μ's were converted into millisiemens. And as a result, they had 7,500 entries that were incorrect. And they just didn't know. So we contacted them, and they corrected the units. There are more in there currently, so you do have to be careful. These kinds of errors do occur. Another thing is it's really important, the knowledge that you have is very important, especially with respect to local matters. So you'll know a place better than anyone else. But in addition, sometimes it's reported whether something is a stream or an estuary. So although this is a gray dot, it might seem like how could it be next to a purple dot, which would be a very low conductivity stream. These gray dots could be real. In this case, it's an estuary. So these very high values of over 50,000 microsiemens per centimeter are probably accurate. All right, so the next thing behind this is how do we predict what the background conductivity would be? So the way we did this was with a random forest regression model. The first thing we did was we identified sites that are likely to be least impacted by human disturbance. And these are the points shown on the map on the left. And the size of the dots indicates how many repeat samples came from that location. And we use these dots in a regression model to make the prediction of conductivity in the map that you see on the right, where the cooler colors are lower conductivity and the hotter colors are higher conductivity. And this is natural, expected to be natural in the stream because the model was made from these reference samples. And you can see that the data set was very large initially, but after we culled it down, it was still big, but nowhere near 1 million. So we used over 11,000 samples in the training data set, and then we validated it with a smaller data set. So the way the random forest model works is there are many parameters that go in to the model, and then tree breaks are made based on what is the best predictor of the measured conductivity at those reference sites. So in this example, to kind of give you a sense, we have a mountain, and we have places where the conductivity is high and places where it's low, and then we can use that information to predict where it will be low and where it will be high. And you can see the breaks here are east to west, and also with the calcium carbonate in the rocks. So the first break occurs here, and then the second break is east to west. Now this is with the original data set, but how do you make more data sets when you only have one data set? Well, what you do is you simply remove some of the sites. So you can see here some of the sites that were sampled are removed, and it creates a new data set from the original data set. And you do this many hundreds and thousands of times. So then you again run the model. This time the breaks fall first on east to west, and then based on calcium oxide concentration in the geology. and you end up with a different tree. So you make lots of these little trees, as you can see here, and then you take the average predictions from these trees to make a final model that predicts what the conductivity would be in the stream, or if it's total phosphorus, what's the phosphorus that is predicted to be in a stream naturally. So with this random forest model, what did we use to put into the model in the first place? We use data that has been collated in StreamCat, and you can access it from this link, and all of the NHD plus stream networks across the United States and territories. And then what we did was we then looked at all of the different parameters that could be used. And sometimes the data was collected over multiple observations. So we had both a spatial and temporal data. And these are the variables that were selected. So you can see the rock percent calcium oxide was the strongest variable in the model. Rock percent sulfate was next. Atmospheric calcium deposition. And then we have things that have to do with the more local conditions like the water table, soil K factor, percent clay, soil permeability. Then we had variables that had to do with the vegetative cover. We had variables, which you can see in the blue, that had to do with precipitation. And you can see the red ones here have to do with temperature. The ones that are in the little hatch boxes here are ones that had multiple measurements through time, and we could use it then to tie more directly to changes such as drought, which would happen over a period of time. Here's the model. It's always nice when you get a good fit. And you can see the R-square and the RMSE are very good. Then when we ran it with the additional validation data set, you can see we have a pretty good fit. Not as perfect, but not bad. And if you take out these few points, then you have a really good fit. So we're pretty happy with the model, but all models, as you know, are not the same thing as a measurement. Here's the model performance on a map. Here are all those sites that we had as reference sites where we had the actual measurements. And you can see that at all the green points, the predicted conductivity was within 100 microsiemens, which is really pretty good. And the red dots are, less than measured, and the yellow dots, more of them you can see through here, they were more than 100 microsiemens was the actual measured. So how can we use this on a national scale? One way we used it was to look at how background is expected to change with drought. And what we can see is that there's very little change. There's some change, but not huge. And this is encouraging because it says that if you are in a reference type condition and there are no inputs, then it's likely that the salt concentration in the stream is not going to change too much. In general, less than 170 microsiemens per centimeter. And when it comes to the biology, 100, 200 microsiemens doesn't make too much difference for short term. All right, so let's look at navigation and using this system for national and state level information. When you go to the site, this is the current first screen that you see. That's Freshwater Explorer Beta when the phosphorus background model is added, this number will change. This is the link to the site. Currently, this Freshwater Explorer is only available with a password-protected system at EPA. All of the participants' names will be given on today's call. Will be given an invite to join the GEO platform so they can access this tool. When you get that information in your mailbox, you simply go in, establish a password, and then I can give you access. And when you click on this link or you type it into your browser, you will then go directly to the Freshwater Explorer. After you scroll through the initial explanations, you will get to this first screen, and what you can see is that familiar map of the background conductivity. Because we can't see all the streams at this resolution, it's just showing you what the little drainage areas conductivity is expected to be. There are instructions on the left. There's across the top different tabs that you can select. This would show you what's the background conductivity expected to be. This is the measured conductivity from the water quality portal. This, if you only want to look at USGS's NWIS data set, you can click this link. If you want to see our model validation, it's here. And if you want to look at the phosphorus data, you click this one. When you zoom in, what you can see is the streams start to appear as a network, and they're color-coded. So these bluer lines are cooler, so they're going to have lower conductivity. The yellow ones, the warmer colors, are going to have higher natural background conductivity. And the legend can go up and down. You can also see some other tabs up here. If you want to access the data itself, you can click on that tab. So as you zoom in, if you click on a particular stream segment, what will happen is you will get a pop-up box, and this tells you that the predicted background for this little stream segment is 603.7 microsiemens per centimeter. If the stream has a name, it'll indicate the name. If you go to the measured conductivity and you click on a dot, what will come down is another pop-up box. It'll identify the name of the stream, who collected the data. It'll show you the mean, median, max, and min data, and what was the last measured conductivity at the site, and what was the date of that collection. If you scroll down a little further, you can also see what was the predicted conductivity for that site if it was undisturbed. And this is a pretty good one. This one is a nice blue dot on green, so it's matching what's behind it. That means this stream is, or this location on the stream is in good condition compared to what its background is. Here's just a screenshot of the measured total phosphorus. You can see the patterns kind of similar, with some areas having lower phosphorus on the coast, higher in the agricultural areas. And it operates the same way. You can click on a dot and it will pop down and tell you what the phosphorus content was measured at that site. If you scroll below or you hit the data access, you will get this screen. And what it shows is how to access the actual data that's in the Explorer. So if you want to remove data and get the tables, you just click on one of these, and then it will bring you to the site. Alternatively, you can click on these links that I've copied here, and it'll do the same thing. However, again, you need to have access to the US EPA's GEO platform, and we will try to provide that for you immediately after this talk. So here's an example of looking at the national data. If we look at the prediction, we can see it's predicted to be low in these areas. And what you can see in the actual measured data, these are all the sites that are within 100 microsiemens of the prediction. And you can see we have, thankfully, lots of beautiful places across the United States where the water is still very fresh and as fresh as it was predicted it should be. There are some areas that are higher conductivity. You can see there are not so many places here that are as fresh, and that's not surprising if you know these parts of the country. These are the places, if we put a filter on it, to look at where the places is the conductivity 500 microsiemens greater than what we would expect it to be. And here you can see that they're all over the country. Some places even where there is pretty high rainfall. And so those are the places that get kind of interesting. You know, what's going on? Is this natural or not? Is this something that needs attention? So let's take an example. This was given to us courtesy of folks up in New Hampshire. And you can see that I've highlighted a little area near Jackson, New Hampshire, which is near the ski areas. And if we zoom in, we can see that there's a stream here, the Ellis River, and then there's actually another stream running here, but it wasn't on the NHD Plus network. And you can see that there are some purple and blue dots which indicate conductivity is low. We have a purple stream here telling us background conductivity in this area should be very low naturally. But here at these sites, this red site and these gray sites, it is extremely high, higher than even in the ocean. And these gray sites were tagged because the computer program that we wrote said this is so crazy it can't be true. Unfortunately, it was true. So the predicted background for this site was supposed to be about 32 microsiemens per centimeter. This is a granitic area, very low conductivity, and instead it was extremely high. When you zoom in, what you can see is here are the points where the measurements are taken, and this place that I've highlighted in the red is a salt pile. And what was happening is the salt was running into the stream and then into this larger stream, the Ellis River. And what the folks in New Hampshire did, they contacted the highway department. They pointed out the problem. They said, okay, what can we do about it? And what they did is they built a new storage facility where the salt is stored, and they positioned it so that if there is a spill, it would flow into two different streams and not only into one, so that you had higher dilution impact. So here you can see chloride measurements from this stream, and you can see that it was extremely high prior to the construction of the new building and storage of their salt for road treatment. And then you can see that afterwards it was extremely low. So at this point, the state is waiting to monitor a little bit longer just to make sure, and then they expect to be delisting it from the 303D list that they send in to EPA. So what's next? What else could we do? And I'm sure that you're thinking, oh, they should add this and they should add that. And you can think of other things you'd like to have on here and ways that you could use it beyond these few examples I've given you today. And you're right, there's more that could be done. So here's one example. This is not available yet for everybody, but it's intended to give you a sense of what could be done. We've been working with the Arkansas DEQ, and here you can see a different version of the Freshwater Explorer. We have phosphorus conductivity and a new tab, Explore Additional Data. When you zoom in, it's the same sort of things. You see the network of streams. You can click on it and get data. But you can also choose what you want to see. So you have more flexibility. It's not prescribed as it is in the current Freshwater Explorer. Then the other thing that they have is they can choose other coverages to look at. So in this area, these are 303D listed streams that are highlighted in yellow. You can see the measurement dots, and so you can start to ask questions. You can click on the yellow outline here, and it will tell you what the stream has been listed for on the 303D list. And then you can click on the measure dots to see if that's been captured and what kind of other information there might be to address these problems. You can also select an analytical tool and select specific sites and then plot them so that you can see that at this site, this is the conductivity maximum, minimum, and median that was recorded, and that it goes down at this location and then back up again here. So what's the take-home messages here? First of all, that the EPA Freshwater Explorer allows you to assess areas of interest. The water quality exchange contributors can spot data integrity issues and make corrections and see these errors that are in the portal. They can share watershed and regional stories by looking at this information, pulling off the imagery. We will be adding the background nutrient estimates in 2021. We're in the process of making the model to estimate those, and those will be added. And I think what the Arkansas work shows is, here's the basic framework, and now, it's very easy to potentially individuals to download this from the site and create a smaller ones for each state or project. And so we say, go ahead, download it, add your own data, add other coverages, so that you can increase the analytical potential with other spatial information. And of course, we're hoping you will provide us with feedback on how to improve the tool. So I'm keeping it short today so that you'll have plenty of time for questions. This is me, Susan Cormier, and you can reach me at my EPA email, or you can call me, and it will route to my mobile phone. And this is a blanket statement. No matter what your problem is, reach out to me, and I will try to get it resolved or answer your question. I want to give special acknowledgments to Chris Wharton at Tetra Tech, who was really instrumental in building the Freshwater Explorer, John Olson from California State University, who developed the random forest model for prediction of background conductivity. I want to thank Matt Wood from New Hampshire Department of Environmental Services for providing some of the slides and making sure I told the story right about New Hampshire. And Joe Martin from the Arkansas Department of Environmental Quality for helping us with the slides from Arkansas. Again, here's the link, but as I've mentioned before, you need to make sure that you ask for your GeoPlatform password, and then you can access the system. And that's it for today, and I'm open for questions.